Okay, so this will be a continuation of my complex analysis playlist. In this video, I'm going to be talking about more about linear maps, except now I'm not going to be dealing with um, quote-unquote simple functions. They're going to be slightly more complicated functions. Now, I'm going to be sticking with Cartesian coordinates for the time being, and basically I'm going to show that when you have a line such as this in the xy plane, when you map it to the UV plane, it actually turns out to be not what you would probably expect. And I'll just get right into it so we can understand how the problem works, and then from that we can try to understand what the graph looks like and why it looks the way it does. So let's suppose we have a function f of z equal to z squared, and remember that the function takes a complex number and maps it to another complex number. We're mapping from c to c, and then of course f of x I y is equal to maps to f of u v. And so basically, if you remember from my previous videos, anytime you see z, you can always write it as x plus iy, and I've said this many times, it's one of the golden rules of complex analysis. So let's just get right into it. So x plus iy squared, well, that's going to be equal to x squared minus y squared plus 2xiy. Now, I memorized this expansion, but really if you work out the algebra, you'll see this is exactly what it looks like if you don't believe me. But this is very good to know that x plus iy squared is equal to x squared minus y squared plus 2xiy. Now, I also mentioned in the previous video that we're going to need to break apart these complex functions into the real parts and the imaginary parts. So how do we do that again? Well, u is going to represent the real part of the function, and it's going to be equal to x squared minus y squared. And that's because neither x squared nor y squared here, they don't have an I multiplying them. Basically, any term that does not have the I goes into the u. So u is the real part, and then the v is going to be equal to 2xy. That is the imaginary part, and again, because the I is multiplying 2x and the y. Now, suppose we have the line y is equal to 2. Well, how exactly do we go about mapping this into the u and the v plane? Well, it's maybe what you're expecting. All we're really going to do is we're essentially going to do, well, actually, before I even do that, let's just kind of get a full understanding of what exactly we're asking. So let's suppose we have something like, say we have, I guess, A takes x and y, and what we want to know is we have the line y is equal to 2, and what does that map look like in the UV plane? Now, this is how you do it. This is how you essentially solve the problem. So what we're going to be doing is we're essentially going to take the 2 and plug it into the v. And so we're going to have v is equal to 2x times 2. Because remember, the y is equal to 2, and here we have 2xy, so we have 2x times 2, and so v is just equal to 4x. Now, if we want to know what this looks like in the UV plane, all we really have to do is to solve for x here. So we're going to have x is equal to v divided by 4. Now, what can we do with this? Well, we can say that now u is equal to, we plug in the v over 4 squared for our u, and we have minus y squared. And so, whoops, does not look like a very nice y, not very neat. And so we're going to end up getting u is equal to v squared over 16 minus y squared. That's essentially what we're doing. Now, this is obviously very messy, so I'm going to go ahead and erase some of this stuff, some of this work. Okay, so yeah, it's not particularly the neatest erasing, but okay. Anyway, so we have, let's say u is equal to v squared over 16 minus y squared. And remember, all we really did for that is we plugged in 2 for the y, solved for the v, and then plugged the v back into the u. So first you gotta plug in x or y, because sometimes this could have been x is equal to 2, in which case you'd have a line like this. That would be this line right here, would be x is equal to 2, and you follow the same procedure. All we're really going to do in that case would be plug in x equals 2, and then follow the same idea. So plug in x or y. And then now we're going to solve for x or y. Actually, let me word that a little bit differently. So once we have the x and the y, we essentially have v is equal to some x or y. And what we have to do is we essentially have to say x or y is equal to something going on with v. Like over here we had v squared or v over 2 squared. And so essentially all we're really doing is we're having the x or the y, and we're setting it equal to v. That's step 2. And then step 3, which I'll get into now, is you plug in for u. And that's an interesting way of saying it. But basically, so what we do for the u, we essentially just take our function was v over 2 squared, and we take this and we plug it into there. That's we take this, plug it into here, and we get this. Now, what does this look like to you? This looks like a parabola. This is essentially what you get. So essentially, this is not the neatest graph. I'm going to draw -2 right here. So really, our mapping, very crude, but essentially this line here, y is equal to 2, maps in the UV plane. It actually maps the parabola. And you'll see, erase that part, and you'll see that basically any time, typically, when you have lines map to parabolas in the UV plane. And that's a little weird, but really, if you follow these steps, I could have y is equal to 3, y is equal to 4, and in general, when you have a line, it maps to the parabolas. And you probably can, you probably can prove this to yourself if you probably plug in some arbitrary integer, or really any real number, and kind of follow this procedure. You'll see that you're just going to end up getting parabolas after parabolas after parabolas. So the lines map to parabolas, which is a very interesting way of thinking about it. And so let's say, so really our final, actually, I'm not even going to say A, it might be a little bit confusing. So our f of w, which is essentially the result of our mapping, our output, is we can say it's going to be uv such that u is equal to v squared over 16 minus y squared. That is essentially our, that is our result. So to recap, there's a lot of stuff in this video, but basically all we're really doing is we have some kind of function, we have some kind of mapping. Here we have z squared. If I had z cubed here, then, like let's say I had something like this, if I had something like, or z to the 4th even, z to the 4th, you do this, and of course now your u and your v would be different functions altogether. But you still follow the same procedure. If it was, y is equal to 2, but the mapping that you're required to do was z to the 4th, you follow the same procedures, except that your u function would be different from this, and your v function would be different, but you'd still plug in your y, and then you solve for the v, and plug that back into the u, and that will give you your mapping. Now, of course, one example is not enough to get this idea, to really have a solid understanding of what's going on here. So I'm going to be doing a couple more examples in previous videos. I'm going to be working only with Cartesian coordinates for now. I will eventually move to polar coordinates, and after all of that, I'll get into complex limits. But anyways, that's just coming attraction. So I hope you guys enjoy, and I'll see you guys in the next video.